Welcome to the third session. This session is handled by Patricio Frosini, Associate Professor at the Department of Mathematics of the University of Bologna. He received a PhD degree in mathematics from the University of Florence in 1991. He is mainly interested in the study of topological and metric properties concerning topological space and manifolds endowed with Rn-valued functions. He has introduced the concept of size function, precursor of the concept of persistent homology. We cordially invite you, sir, to deliver the talk.
Thank you so much for your presentation and for inviting me to this interesting conference. I'm going to share my screen. Okay. I hope that you can see my screen clearly. I will speak about group equivalent and expansive operators. Please, in case of questions, just speak without writing something in the chat, since I could forget of having a look at the chat during my my talk. So I start, and my purpose is the one of introducing the theory, the basics of a theory of group equivalent and expansive operators, making clear their use and their potential in machine learning. My first, let me say, 15 slides will concern the philosophy, epistemology of group equivalent and expansive operators. After that, I will describe some mathematical results. Okay, so I start from the description of a key role of observers in data analysis. We know that in many cases, many different situations, data are expressed by functions. For example, this happens when we consider electrocardiograms. They can be seen as functions from the real numbers to the real numbers. Or when we consider gray level images, since they can be seen as functions from the real plane to the real numbers, or maybe a closed interval. And another example is given by computerized tomography scans, where we have a helix going around the body and producing a function. The machine produces a function from this helix to the real numbers. Obviously, I'm not saying that every kind of data is a function, but in many cases, we have the data are represented as functions. And for example, even if we consider a graph can be considered as a function. It is the adjacency matrix, okay? Anyway, we are in this talk, I will speak about data represented by functions. Okay, I will confine myself to consider real valued functions, but we can also consider vector valued functions defined on a set X. Please pay attention. At the very beginning, we have no structure on the set X. We have just the measurement, the function, okay? We will denote by capital Phi the set of admissible data. Admissible data means the set of measurement that our measuring tools, our measuring machines can produce. For example, if I take an exponential, this cannot be seen as an electrocardiogram. Okay, so we have to say, I just admit this kind of signals in my game. And this set of admissible signals, admissible data, is denoted by capital Phi in this talk. Okay, For example, when we consider an image, we usually assume that the function representing this image is a bounded function, okay? We start by saying something about equivalence between signals and similarity between signals. In this talk, I will consider these definitions in form, let me say, in some sense, formal definition, in some sense, not so precise. But anyway, what does it mean that two signals are equivalent to each other? If I take the signals phi1, phi2 as functions from a domain X to the real numbers, we can say that they are equivalent with respect to the action of a group G of permutations of the domain X if there is a permutation of the domain such that phi1 is equal to phi2 composed with a permutation. When I say permutation, I use this term in order to allow any possible transformation of a domain, but we are usually interested in particular kinds of permutation. For example, if we are considering images, we are probably interested in rotating these images, translating these images, this kind of things, not every kind of permutation. But in general terms, we can say that the group of transformation we are interested in is a group of permutations of a domain. When we say that the signals are similar to each other, we mean, with respect to the group G we have chosen, we mean that the norm of a function phi1 minus phi2 composed G is small for a suitable permutation, a suitable element G in our group capital G. Before going on, I have to introduce the formal concept. And this formal concept is a concept of natural pseudo-distance associated with a group G. What is the definition of this natural pseudo-distance? Now I have to assume that X has a topology. I will go back to the assumption that there is no structure on X, but in order to introduce the natural pseudo-distance, I have to assume that now X is a topological space. And I also take a subgroup G, capital G, of a group of every possible homeomorphisms from X to X. Okay? I choose this group, and now I say that the natural pseudo-distance between two signals phi1 and phi2, seen as continuous and bounded functions from X to R, we define this value as the value infimum, varying the possible transformation in our group capital G of a max norm distance between phi1 and phi2 composed G. For example, I give you two images, phi1 and phi2, and I ask you, are they similar with respect to the group of translations? You take the two images, you translate the second one, and you try to have a good match with the first one. The infimum of the distance between these possible matchings is the natural pseudo-distance with respect to the group. In this case, the group of translations, but the group is a variable in this game. Okay? So we have introduced the natural pseudo-distance between signals with respect to a group. I recall that the pseudo-distance is just a distance when we remove the assumption that d of x1, x2 equal to 0 implies that x1 is equal to x2. So we can have two objects that have a vanishing distance, but they do not coincide. Okay, this is natural pseudo-distance. Why did I introduce this concept? Since we could look at the natural pseudo-distance as the ground truth in data comparison when data equivalence is expressed by the group G. Okay, so in this game, two signals are equivalent to each other, are similar to each other, if their natural pseudo-distance with respect to the chosen group is small. there are some trivial properties of a network pseudo-distance. There are two limit cases when we consider this concept. We can take the smallest possible group, G, that is the group just containing the identity, okay? And in this case, the network pseudo-distance becomes just the max norm distance. When we consider the largest possible group, the group of any possible homeomorphism from X to X, we have this distance. And in the middle, we have the other values of the network pseudo-distance. When G is a subgroup, G1 is a subgroup of G2, we have that the order reverses. The network pseudo-distance associated with G2 is smaller than the network pseudo-distance associated with the group G1. This is trivial, okay? Just to explain what the network pseudo-distance is. And I have to add that we usually restrict the network pseudo-distance to phi times phi, where phi is a bounded subset of a set of continuous functions from X to R. Okay, now I have to say something that is important in my opinion. Data are processed by observers. Data have no meaning at all if no observer elaborates them. We need observers in order to compare data. And what is an observer? An observer is an agent that transforms data into other data. I add with respect to the action of some group. Okay, it is important. It is a key point to observe that observers are variables in data analysis. Data interpretation strongly depends on the chosen observer. If we change the observer in the presence of the same data, we can have completely different reactions, okay, and judgments and classifications. So, the important concept, in my opinion, is not the concept of data. It is the concept of the pair data-observer. We are hardly ever interested directly in the data, but in the relationship between the data and the observer. We are interested in a relation. What interests us above all is the behavior of observer in the presence of the data. For example, we can consider the situation. A patient is usually not interested in the picture of her skin lesion, but in the diagnosis her dermatologist can make from this image. The cases in which the interest in data seems central are those in which the observer's way of reacting is tacitly shared. For example, if I say I am interested in the length of a table, I can forget about the observer if I'm not interested in quantum mechanics, okay? Since there is a procedure and every observer behaves in the same way, and I can get approximately the same result. But also in this case, we have observers. The important fact is that the choice of observer in this case is not so important, since the observer's way of reacting is tacitly shared, okay? But in any case, the important thing is the pair, data-observer. I have to add that observers are often more important than data. Data analysis strongly depends on the chosen observer. If data analysis were not dependent on the chosen observer, then physicians' diagnoses would always be identical, scientists would always see the same causes for each phenomenon, and all people would agree in judging who the heroes and villains in a movie or a political event are. But this is not the case. It is indeed well known that different agents can have different reactions in the presence of the same data, and this suggests that data analysis should study the pairs data-observer instead of data alone. All this leads to privilege the study of a form of observers over the study of a form of data. I have to stress this fact. Observers are often associated with invariance groups. For example, if we are interested in comparing images of shells, we could think that this shell on the left has the same shape of the shell on the right. Since in this case, we think that when we rotate a shell, we preserve the shape. So in this case, we could consider as an invariance group the group of containing the translations and rotations of a plane. But if we are interested in letters, we cannot consider the same group. In this case, rotations should not be allowed. And maybe we could consider a different group, maybe the group of translations, maybe we could allow for deletions, but not rotations. So in many cases, we are interested in invariance groups, and invariance groups are variables in this game. Now, I have to say something linking observers to equivariant operators. Observers are structures able to change data into other data, and usually do that by respecting some data equivalences, that is, by commuting with some transformations. Just an example. If you are considering blurring of an image, and in order to blur this image, you consider a symmetric kernel, you know that you obtain the same result when you translate the image and then you apply the blurring, or you rotate the image and you apply the blurring. You obtain the same results that you obtain when you rotate the image. You reverse the order. Okay, so you can apply the blurring and then you can rotate, or you can rotate and then you can apply the blurring, and you obtain the same result. In this case, we say that our operators is equivariant with respect to the action of a group. What I say is that at the first approximation, observers can be represented as group equivariant operators, GEOs. Okay, but in this talk, I will give some results on the theory of group equivariant non-expansive operators, that is, GEOs. Why non-expansive? It is clear that we are interested in equivariance. It is quite well known in machine learning. Okay, there is a lot of research about equivariant operators. Since if we know that there is some invariance in some problem, it is important that we insert this information in, for example, in our neural network. Okay, since we know that. But in several cases, it is important to consider non-expansive operators. Why? Why? There are two reasons, at least two reasons. The first reason is that observers are often assumed to simplify the metric structure of data in order to produce meaningful interpretations. And simplifying the metric structure means non-expansivity of the operator. Distances do not increase. And then there is a topological reason, a mathematical reason. Non-expansiveness guarantees good topological properties, and I will say something about this. So, summary of this list of 15 slides introducing the topic. This mathematical model is based on these assumptions. First of all, the space of observers, that is GEOs in this language, is often more important than the space of data. The study of the space of observers requires the development of a new topological geometric model. This new model could be of great use in data analysis when the role of the observers is not negligible. These assumptions suggest we move from topological data analysis to what we could call topological observer analysis. the form of a space of observers. This is important. Now, some information about the topological and metric basics in the theory of genius. As I told you at the very beginning of a game, we have just measurements. We have a machine producing functions, and we have no structures at all. The domain of this function has no structure at all. It is not a topological space. Okay, we have just measurements on this space. So now we assume that X is just a non-empty set. And now we consider the space capital Phi of admissible functions. For example, functions that can be interpreted as images. Okay, and this is a topological space with respect to this to the max norm. Okay, we have a distance between functions, even if X is not endowed with a structure. So we have this distance d phi that is just the max norm. We can see X as the space where we can make our measurements, and capital Phi as the space of all possible measurements. We will say that capital Phi is the set of admissible functions, and in other words, capital Phi is the set of all functions from X to R that can be produced by our measuring instruments or by our observers, giving us the results of their action on our data. Okay? For example, a Gray level image can be represented as a function from the real plane to the closed interval 0, 1. In this case, X is the real plane. Now, the concept of perception pair. What is a perception pair? Let us consider a group G of bijections from X to X, that is permutations of X, such that we have this property. If we take an admissible signal, phi, and we compose phi with an element in G, we obtain another element in capital Phi. So the composition of an admissible signal with an element of capital G produces another admissible signal. In this case, we say that phi G is a perception pair. Okay, so saying that phi G is a perception pair is equivalent to say that phi is stable under the action of a group G. The choice of a perception pair states which data can be considered as legitimate measurements, the functions in capital Phi, and which group represents the equivalence between data, the group G. To proceed, we need to introduce suitable topologies on the domain X and on the group G. Before doing that, we recall that the initial topology on X with respect to capital Phi is the coarsest topology on X, such that every function phi in capital Phi is continuous. This is the initial topology. Now we can consider on X this pseudometric. What is the pseudo distance between 2 points in the domain X? It is the supremum varying the admissible signal of a distance, the Euclidean distance, I mean, between phi of x1 and phi of x2. And since we have a pseudometric, we have also a topology on X. X is now a topological space. Please pay attention. The use of this pseudometric implies that we can distinguish 2 points only if we have a measurement that takes these points to different values. This is the philosophy in this game. You cannot say that 2 points are different if you have no measurement saying that they are different from each other. Okay? This theorem holds. The topology we have introduced is finer than the initial topology on X with respect to capital Phi. If capital Phi is totally bounded, then the two topologies coincide. So, after choosing this pseudometric, we have these properties. First property, every function in capital Phi is non-expansive and thus continuous. Each function is continuous in this game due to the choice of our topology on X. And if capital Phi is compact and X is complete, then X is compact. So we can assume that X, if capital Phi is compact, we can always assume that X is compact, since in the case it is not, we can complete it. Okay? So now some magic happens. Each bijection is an isometry. Why? Let us consider the group of every possible bijection from X to X, okay? And that is permutations of X. And let us confine our attention to the subgroup of these permutations containing just the permutations that preserve capital phi. This means that when we take an element in this new group, we have that when we compose an admissible signal with this element G, we obtain another admissible signal. And this happens also for the inverse of the permutation G. So this is a subgroup of a group of permutation. And we can do the same for the group of homeomorphism, obtaining the subgroup of phi preserving homeomorphisms of X. And we can do the same for the group of isometries of X. So obtaining the group of phi preserving isometries of X. Now, something interesting happens. These three groups coincide. The group of phi preserving permutation of X coincides with the group of phi preserving homomorphism, and this coincides with the group of phi preserving isometries. And this is a consequence of a topology we have chosen on the domain X. And it is also the reason for choosing that topology. Now we can also consider a pseudometric on the group G. And you can imagine what is the definition. Since the definition must come from our assumption that at the very beginning of a game, we have just the measurements. So we can compare the permutations in G only by referring to our measurements, okay? So what is the distance between two permutations, G1 and G2, belonging to the group capital G, which is a subgroup of the group of phi preserving homomorphisms? This pseudo distance is by definition the supremum varying the signal of the max norm distance between phi composed with G1 and phi composed with G2. In order to make clear this concept, let me give you an example. Imagine that we have chosen a trivial set of admissible signals, the set of constant functions on our set X. In this case, there is no way of distinguishing the elements of G, since when we compose the constant function with a permutation, it doesn't matter what this permutation is, which permutation we have chosen. We have that phi composed G1 is equal to phi composed G2. And so the distance between two permutations is always vanishing. So if the set of measurements is trivial, the structure on the group is trivial, okay? But in the usual case, we have a richer set of possible measurements. Okay, theorem, G is a topological group with respect to our pseudometric, and the action of G on the set of admissible signals by right composition is continuous. So we have a good mathematical setting in order to proceed. And also we can say that if capital phi is compact and the group G is complete, then the group G is compact too. So we have some results about this. Now we can formalize the concept of GEO, group equivalent operator, and GENIO, group equivalent non-expansive operator. So let us consider two perception pairs, phi G and psi H. So we have a set of admissible signals phi on a set X, on a domain X, and another set of admissible signals on another domain Y. Okay, and we have two different groups, G and H. And now we have, in order to proceed, we have to fix a homomorphism T from the group G to the group H. We have to say which permutation on Y corresponds to a given permutation on X. Okay? We say that each function f from capital phi to capital psi is a group equivalent operator, that is a geo, if this equality in yellow holds. That is, we can, that is, the composition, the action of a group commutes with the operator when we use this homomorphism T. And we say that f is non-expansive if the max norm distance between the signals we have in the image is not greater than the distance between the original data before applying the operator. When we have that our geo is non-expansive, we say that this is a group equivalent to an expansive operator, a genio, associated with a homomorphism T we have chosen. But in order to proceed, we have to give you an example. So let us assume to be interested in the comparison of the distributions of temperature on the Earth, okay? And also assume that we are not able to distinguish the countries. We are just able to distinguish on the Earth the North Pole and the South Pole, and the point N and S, okay? We can see two different, in the figure, two different distribution of temperature is in colors, okay? Now, we can define two different perception pairs and the genio. What are our perception pairs? Phi G, the first perception pair, is given like this. We consider the domain X given by the surface of the Earth, S2. And we consider on X, defined on X, the set of capital Phi of all one Lipschitz functions from S2 to a fixed interval, closed interval AB, where A is the minimum possible temperature that we can measure on the Earth, and B is the maximum possible temperature, okay? Each distribution of temperature is a function in capital Phi. And now we consider the G as the group of rotations of the Earth. We can rotate the Earth around the axis North Pole, South Pole, okay? Obviously, the action of group G preserves capital Phi. When we rotate a one Lipschitz function, we obtain another one Lipschitz function. And the pair Phi G is our first perception pair. The other perception pair can be obtained like this. We consider the equator Y of the Earth, which is a circle S1, and the set capital psi of all one Lipschitz functions from the equator to the closed interval AB. And then we take H, the group H, equal to the group of rotations of the equator. Okay, so we have two perception pairs, Phi G and Psi H. Now we can consider this simple example of genio from Phi G to Psi H. T, the homomorphism T is quite trivial. What is the rotation of the equator corresponding to the rotation of the Earth? It is quite natural. If we rotate of alpha degrees the Earth, the corresponding rotation of the equator is the rotation of alpha degrees of the equator. Okay, so T in this case, in this simple example, is indeed an isomorphism. Okay, and how can we define our genio F? F of phi is a function defined. Phi is a function defined on the Earth. F of phi is a function defined on the equator. Is a function psi defined on the equator. And this function takes each point y belonging to the equator to the average of the temperatures along the meridian containing y. Okay, so for each point in the equator, belonging to the equator, we compute the average of the temperatures described by phi along the meridian. We can easily check that F verifies the properties defining the concept of group equivalent non-expansive operator with respect to the isomorphism T. So what happens? In plain words, our genius simplifies the data by transforming temperature distributions on the Earth into temperature distributions on a smaller manifold, that is the equator. Okay? And this is the meaning of the use of genius, simplifying data with respect to the action of a group. Now we have two good news for applications, represented by two key results. Let us assume that a homomorphism T from G to H has been fixed, and we consider the two perception pairs phi G psi H. We can define a metric d genio on the set of all genios from phi G to psi H by setting that the distance between the two genios F1 and F2 is the supremum varying the signal, the admissible signal in capital phi, of the max norm distance between F1 of phi and F2 of phi. Please remember that capital phi and capital psi are not vector spaces. They are usually just bounded sets. Two theorems. If phi and psi are compact, then the space of all genios is compact too. This is quite important and depends on our choices about metrics. Okay? We are saying in practice that when the spaces of data are compact, the space of observers is compact too. This is quite weird, since in real life, we know that data can be quite simple and observers can be quite complex. Or it can happen that data are quite complex and observers are quite simple sometimes. But this theorem says that when the space of data is compact, the space of observers is compact. This weird statement depends on our mathematical choices. And it is important since compactness means that you can finitely approximate objects. So we can say that if the spaces of data are compact, we can approximate with a finite set the space of observers. This is quite important. And this result strongly depends on the assumption of non-expansiveness of genius. This is the reason, the topological reason for adding the assumptions of non-expansiveness to group equivalent operators. Furthermore, if the space capital psi is convex, then the space of genius is convex too. That means that when we consider convex combination of genius, we obtain new genius. This is important for applications. So now, after saying something about the definition of genius and about the topological and geometrical properties of genius, I have to say something about the way we can produce genius. There are some elementary methods to build genius. For example, we can build genius by composition. If we have two composable genius, F1 and F2, they are genius with respect to the homomorphisms T1 and T2, then the composition F2 composed with F1 is a genius with respect to T2 composed with T1. This is trivial, okay? So the composition of genius produces new genius. Another simple proposition is this one. Assume that we have a one Lipschitz function L, okay? And also assume that we have n genus F1, Fn from phi g to psi h. Then we can use this one Lipschitz function to combine our n genus and to obtain a new operator that is still a genio. Particular cases of the application of this proposition are illustrated in the next three propositions. First of all, when we consider n genius F1, Fn, the maximum and the minimum between these genius is still a genio. This means that there is structure in the space of genius. The space of genius is a lattice. Then we have that when we translate a genio, we obtain another genio. And finally, I repeat, when we combine by a convex combination some given genius, we this way, as expressed in this formula, okay, we obtain a new genio. For example, if I am in the space of genius, I have three genius, okay? I can say that the triangle described by these three vertices is made of genius. So from just a finite number of genius, we can produce an infinite number of genius. But these are trivial methods to produce genius. I would like to illustrate a non-trivial method, okay, that is based on permutant measures. In this case, I have to assume that phi is the particular case of admissible signal. In this case, capital phi is the set of every possible function from a finite set x, okay, x contains x1, xn, to the real numbers. So we have, in this case, that x is a finite set, and we take any possible function from this set to the real numbers. So in this case, capital phi is not compact. Okay? Now we take a subgroup G of a group of every possible permutations of x. Okay? And G is our invariance group. Definition: a phi, we allow the possibility that the measure is negative. Okay? A finite signed measure mu on the group of permutations of x is called a permutant measure with respect to the action of a group, capital G, if every subset H of the group of permutation is measurable and mu is invariant under the conjugation action of G. That is, when we measure this set of permutation H, we obtain the same number that we obtain when we measure the new set GH, the inverse of H. Okay? When we have this kind of measure on the set of every possible permutation, we say that we have a permutant measure. Why is this permutant measure important for the theory of geo and genius? Because this proposition holds, if mu is a permutant measure with respect to capital G, then this map that you can read in red color is a linear geo. What does we mean by writing this map? This map is given this way. We have a function phi. We have to transform this by the geo. What is the result of this operation? The result is given by this formula. We compose phi with the inverse of each element in our space, the inverse of each element in our space of permutations of x. Okay? We obtain a new function, and we give to this function a weight, and the weight is the measure of h. We take the summation, and this new function is a genio. I mean, the operator taking phi to this new function psi, not a genio, a geo, a group equivalent operator. Okay, and it is a linear geo. Let me give you an example in order to understand this definition. Let us consider the set X of the vertices of a cube in R3 as you can see in this picture, and the group capital G of orientation preserving isometries of R3 that takes X to X. So we admit just the transformation, the isometries of the space that takes this set of vertices to itself. Okay? This is our group G. Now we can consider the three planes, pi1, pi2, pi3, that you can see in the pictures. These are the planes that contain the center of mass of X and are parallel to a face of a cube. Now we consider the orthogonal symmetries H1, H2, H3 with respect to pi1, pi2, pi3. Now we can define the permutant measure mu on the group of permutations of this set of 8 vertices by setting that mu of H1 is equal to mu of H2 equal to mu of H3 equal to a positive real number C. And we set mu of H equal to 0 for any other permutation of X. Okay, this is our definition. Please consider this fact. The group G contains 24 elements, but the support of a measure is small. It contains just the free permutation H1, H2, H3. This is quite important. It is important to observe that G can be quite large, and at the same time, we can have that the set H1, H2, H3 is small. This is important for application. Since now we have to integrate on H instead of integrating on G, that can be large. Okay, so this representation theorem holds. This is an important fact about permutant measures. Let us assume that capital G is a subgroup of a group of permutation of X. And let us also assume that G transitively acts on the finite set X. What does it mean? You know that a transitive action means that when you take 2 points in X, you can always find at least one transformation that takes the first point to the second one. It is the property defining a transitive action. Okay, when we have that G transitively acts on the finite set X, and F is a map from the set of functions from X to R to the same set, okay, we assume this, okay. Then we have that the map F we are considering is a linear genio from Rxg to Rxg with respect to the identical homomorphism from G to G, if and only if a permutant measure mu with respect to capital G exists, such that our operator can be expressed in this way, the way I have illustrated before. And we have the total mass of our measure is less than 1. So the procedure based on the permutant measures is able to produce any possible linear genio, but it requires not the integration of a group G, but the integration on the support of a permutant measure, and we know that it can be quite small. Okay, further details can be found in this preprint that I will recall at the end of my talk. Now, how can we use genius in applications? I will give you 2 examples of application, a toy example and a real application. The toy example is this one. It concerns the comparison between real dice and fake dice. What do I mean when I say real dice? A real dice is the die that you can buy on the market, the usual die. In the usual die, when you sum up 2 opposite faces, you get 7. You always get 7, okay? But we consider also fake dice, where you can recognize in this image, for example, that 4 is not on the opposite of 3, okay? So the property I have described does not hold anymore. Okay, now we consider what is our experiment. We produced 10,000 dice, a training set of size 7,000 and a test set of size 3,000. And then we applied principal component analysis to reduce the information to just 2 numbers for each die. Okay, so we take a die. A die is represented by a function that is the coloring of the faces. It is a function defined on the surface of the die. Okay, this function is described by the long vector of many components. We use principal component analysis, and we reduce this long vector to just 2 numbers. That is a point in the real plane. And we color these points. We color by orange if the pair represents a fake die, and by blue when we think of a real die. So in this picture, you can see the position of real dies and fake dies represented by blue points and orange points in real plane after applying principal component analysis. And you can recognize that if we do not apply Genius, fake dies and real dies are mixed up in the plane in some sense. Now we take the decision of applying Genius before applying principal component analysis. Okay, which kind of Genius? We took the decision of using a convex combination of 3 Genius defined by permuted measure. So we apply the theorem concerning the convexity of the space of Genius and the concept of permuted measures. And we got, in some sense, an optimal Genio. We have a training, and we got an optimal Genio. Now we apply the optimal Genio, and then we apply again PCA, and you can recognize what happens. Now, real dies are well separated from fake dies. And this is the important role of Genius. They insert information in the game. In this case, they say, I know that there is some symmetry in the problem. It is a cube. I know that we can insert this kind of equivalence. So I insert this information, and then applying this information, I apply PCA, and I get this result. So Genius, in principle, are machines to extract information and improve the quality of information. Now, another application, this is real. It is described in this paper, a new machine learning paradigm. It is a preprint. A new machine, a GenioNet, a new machine learning paradigm based on group equivalent on expansive operators, an application to protein pocket detection. In this case, we consider proteins. You know that in proteins, it is interesting to find pockets in Genius. What is a pocket? A pocket is a cavity that is able to host a ligand in order to act on the protein. Okay, so our problem is the one of finding pockets in proteins. In this case, in this image, you can see the protein 2QWE on the left, and on the right, the same protein in more detail. You can find in color the pockets detected by GenioNet. Okay, and inside each spot, there is a number that is the quality, that measures the quality of the pocket. Okay, the search for the pockets was carried out by identifying an optimal Genio in the convex hull of 8 Genios, each focused on a particular property of the pocket. So we started by considering a Genio that was interesting for the geometry of a protein, another Genio that was interesting for from the chemical point of view, another Genio that was interesting from the electrostatic point of view, and so on. And then we mixed these Genios by using our theorem about convexity. And we optimized this Genio, and we obtain a good genome able to finding these pockets. What is the result of this application? The results are displayed in this figure. Each line describes the behavior of GeneoNet and our state-of-the-art methods for finding pockets. Obviously, the higher, the better. Okay, so this blue line is GeneoNet. Okay, and the other lines describe the behavior and the results of our methods. What is the important point? The important point is that GeneoNet uses 17 parameters, 17. While, for example, a convolutional neural network, the convolutional neural network Deep Pocket uses more than 500,000 parameters. What is the reason of this reduction of information? The reason is that genomes are designed in order to extract the important information. Okay. What is the main point in the approach I have described in my talk, based on the use of Geneo in machine learning and for topological data analysis? In perspective, what we are looking for is a good compositional theory for building efficient and transparent networks of genes. Why transparent? Since when we insert a genome, I have described what happens in the case of proteins. We know what this genome does. So it is the use of genomes is intrinsically transparent. Okay. Some preliminary experiments suggest that replacing neurons with genomes could make deep learning more transparent and interpretable and speed up, this is important, the learning process. Obviously, there is plenty of open questions. I have just a list. How can we approximate a real observer, let us say, for example, a physician by genomes, in order to emulate their behavior with respect to data? Can we devise constructive procedures, allowing us to build any possible genome with respect to a given equivalence group? What is the right way of comparing genomes in a topological statistical setting? How should we select representative sets in a probability space of genomes? How can we predict the behavior of networks of genomes and control their actions? How can we evaluate the advantages and limits of an approach to data analysis based on the interaction of genomes and TDA? Okay, if you are interested in this topic, I can give you some references. In this paper, Towards a Topological Geometrical Theory of Group Equivalent and Expansive Operators for Data Analysis and Machine Learning, you can find the mathematical basics for this theory. Okay, essentially an extensive introduction to the topology and of the space of genius. If you are interested in the theory of permutants, that is a concept related to permutant measures, you can have a look at this paper on the construction of group equivalent and expansive operators via permutants and symmetric functions. And finally, you can have a look, if you are interested in the applications, you can have a look at this preprint, a new machine learning paradigm based on group equivalent and expansive operators that is available on the archive. Okay, that's it. I thank you so much for your attention.
Any queries?
Hi, this is Vijay. Can I ask a question?
Please, please.
Yeah, okay. So I was intrigued by, so when we apply priors in deep learning or the introduction of new features in at least a neural network, it seems to, from my high level understanding, it seems to require the notion of a gradient. Now,
could you please repeat the notion of?
A gradient. right?
A gradient. Okay.
Yeah.
Okay.
So this makes it difficult to incorporate discrete kind of elements. So I'm kind of curious, maybe I'm missing something here. So when you have Genios, what would be a notion of gradient here?
Yeah, I can answer you at two different levels. Okay, there is a simple answer based on the fact that when we apply Genius, we usually work with convex hull of Genius. So, for example, in the application I have described previously here, okay, in this application, okay, we consider 8 Genius. So we are moving in a 7-dimensional simplex, depending on 7 parameters, okay? And our optimization is equivalent to moving around in this space depending on 7 parameters, okay? So we are optimizing this by moving in this space. And we can consider a loss function depending on these 7 parameters. So we have a loss function defined on a subset, on a convex subset of R7.
Okay, okay, understood.
This is the simple answer. But there is another answer that is important to say. It is important to recognize that the metric, we are implicitly considering the Euclidean metric in order to compute the distance between this point in R7, okay? And this could, maybe this is not the most suitable metric. We wrote a paper about inserting a Riemannian metric, a Riemannian structure on manifolds of Genius. This is the game in the general case. You have not the space of every possible Genio, not the space of every possible operator, but we have a submanifold of the space of Genius. And there is a way of putting a Riemannian structure, not always, but in some cases, there is the possibility of adding a Riemannian structure of the space of Genius. And now you can follow a gradient that is not the one I have spoken about.
Okay, yeah, that sounds very interesting. Yeah.
If you are interested in this, you can find a preprint on the archive about putting a Riemannian structure on the space of Genius. But the general idea is, do not think of data. Think about moving around in the space of observers. This is important since many people work with operators without thinking of moving in a suitable sub-manifold of operators that share a good property. And this is the reason of greatly decreasing the dimensionality of the problem. This is the reason of, as I have shown previously, this is the reason of having 17 parameters in the application about finding pockets instead of 500,000 parameters.
Right, okay. Thank you.
You're welcome.
Any other queries? No other queries. Thank you, sir. Thank you for the informative session.
You're welcome. You're welcome. Bye.
So forenoon sessions are over. Then the afternoon sessions start at 2:30 p.m. after the lunch break. And one more thing, feedback link is given in the chat box. Please fill that feedback link. Thank you.